How big is the universe? Is it truly infinite, or does it end somewhere beyond our view? Let's explore this mind-bending question over the next 7 minutes. Imagine standing on a beach at sunrise holding a single grain of sand in your hand. Now imagine that grain stretches across the entire Earth. That's how small our observable universe feels compared to what might lie beyond. But first, let's clarify what we mean by universe. When astronomers talk about the universe, they often distinguish between the yet observable universe and the entire universe. The observable universe is all the light and information that has had time to reach us since the Big Bang, about 13.8 billion years ago. Because space is expanding, that sphere's radius is roughly 46 billion light-years. In other words, the edge of what we can see lies 46 billion light-years away in every direction, making the observable universe about 92 billion light-years across. But remember, 46 billion light-years is not a limit on the actual size of the universe. It's simply a horizon, what we can physically observe. Beyond that, light hasn't had time to travel to us yet. So the question becomes, what lies beyond our observable horizon? Is there more universe beyond that cosmic bubble? And if so, does it keep going forever? Or is there an edge or boundary? To answer this, cosmologists look at the geometry and curvature of space. Einstein's general relativity tells us that space can be curved by mass and energy. On the largest scales, scientists measure something called the density parameter, often written as O, omega. If O is greater than 1, space has positive curvature, like the surface of a sphere. If O equals exactly 1, space is flat, like an endless plane. If O is less than 1, space has negative curvature, like a saddle. Current observations, from the cosmic microwave background, large galaxy surveys, and distant supernovae, show that O is extremely close to 1, within only a few parts in 10,000. That tells us our universe is nearly flat. But flat doesn't automatically mean infinite. Picture a piece of paper. It's flat and extends forever. But you could also curl that paper into a cylinder, or even tape its ends to create a torus, a donut shape. In both cases, the paper's surface is locally flat. You can't detect curvature with small measurements, but it's finite, because it loops back on itself. The same could be true of our universe. It might be a giant, flat, three-dimensional torus, a space that wraps around in each direction. If you traveled in a straight line long enough, you'd eventually return to your starting point. But if this is the case, the wraparound size is likely way larger than our observable 92 billion light-year sphere. Since we don't observe repeating patterns in the sky, like the same galaxy appearing in two opposite directions, any finite wrap must be at least several times larger than what we can currently see. So one possibility is an infinite flat universe extending forever. Another is a very large but finite flat universe with a wrapped topology. A third scenario is a closed universe with positive curvature. In that case, space is like a three-dimensional sphere, a three-sphere, where everything eventually loops back. If O were slightly above 1, our universe would be closed and finite, albeit much larger than the observable part. In a positively curved, closed universe, light traveling in a straight line could eventually return from behind if you waited billions or trillions of years. There's also the idea of an open universe with negative curvature, which implies infinite extent, curving outward like a saddle that stretches forever. But because our measurements strongly favor almost exact flatness, a clearly negative curvature seems unlikely, at least within the observable region. Now, how do we know O is so close to 1? One key piece of evidence is the cosmic microwave background, the afterglow of the Big Bang. Satellites like WMAP and Planck have measured tiny fluctuations in that ancient light, revealing how matter and energy were distributed when the universe was only 380,000 years old. These measurements show no significant large-scale curvature. Combined with galaxy surveys mapping millions of distant galaxies, we have a consistent picture of a universe that is flatter than a pancake. But flatness doesn't settle the finite versus infinite question. It only tells us that space is flat within our observational limits. If the universe is infinite, it extends beyond the horizon without ever looping back. If it's finite, the wrap scale is likely many times larger than our observable bubble, so we simply haven't seen far enough to detect it. It's like standing in a dark room. You see the floor around you, but you can't tell if walls exist if they're way beyond the light's reach. Think of it this way. Imagine drawing the Earth on a flat map. Locally, it looks flat. But if your map covered the whole globe, you'd realize it curves and eventually loops at the edges. For the universe, our map is the region we can observe. We can infer that within that region, space is flat. But beyond the observable limits, we have to rely on theory and indirect evidence. Even if the universe is infinite, it still had a beginning. The Big Bang wasn't an explosion from a point into empty space. It was the expansion of space itself. At that moment, the entire universe, potentially infinite, was compressed into a state so dense and hot that physics as we know it breaks down. Then space began expanding everywhere at once. If the universe began infinite, it has always been infinite, merely stretching as it evolves. If it began finite, it expanded from a small finite region to an unimaginably large size. Another twist is the concept of inflation, a theorized period of hyper-rapid expansion in the first tiny fraction of a second after the Big Bang. Inflation can create a universe that appears flat and homogeneous on large scales, even if the parent space is curved or finite. In many inflation models, the universe we see is an almost perfectly flat patch, much like a single tile on an enormous curved dome. That patch could be part of a larger finite structure, or could itself be part of an infinite multiverse. So what does all this mean for us? Whether infinite or just ridiculously large, the universe is vastly bigger than our observable 92 billion light-year bubble. If it's infinite, there truly are endless stars, galaxies, and cosmic regions. In an infinite universe, some argue that every possible arrangement of matter must occur somewhere, maybe even duplicates of our own solar system or planet. Philosophers call this the idea of infinite replication. If the universe is finite but big, that replication may not happen. There might be one unique copy of the Milky Way. The entire universe could also contain regions where physics differs, maybe other pocket universes with different laws of nature. But that drifts into the realm of theory beyond our current ability to test. Strictly speaking, we can only observe within our horizon. Beyond that, it's guesswork guided by the rules of general relativity and quantum mechanics. Either way, the takeaway is the cosmos dwarfs us. Our home, Earth, is 12,742 kilometers wide. The solar system stretches nearly 15 billion kilometers to the edge of the Oort cloud. The Milky Way is about 100,000 light-years across. Our local galaxy group spans millions of light-years. And yet, those scales shrink compared to the observable universe's 92 billion light-year diameter. If space is finite, it could be a few hundred billion light-years wide. If it's infinite, there's no end, no boundary at all. Why does this question matter? It shapes our understanding of everything from the fate of the universe to philosophical questions about our place in an infinite cosmos. If infinite, we live in a boundless sea of possibilities. If finite, we live on a cosmic three-sphere, all within a grand but ultimately bounded adventure. So, is the universe finite or infinite? We don't know for sure. Our best measurements say space is extremely close to flat, which could imply either an infinitely extending space or an enormously large but finite wrapped space. We might push that boundary with future telescopes, CMB-S4 and the Vera C. Rubin Observatory, looking for tiny curvature signatures or repeating patterns. But for now, the universe keeps its secret. It might just go on forever. No matter the answer, what's certain is how much wonder awaits. Whether a never-ending expanse or a cosmic loop, space inspires us to keep exploring, keep questioning, and keep dreaming. That's why we look up and wonder. If you enjoyed this journey, subscribe to Why and tell us in the comments. What cosmic mystery should we dive into next?
Yes.